What's going to happen?
Well, like, so it's the Sunday.
Oh, I think that might not even count.
Rerunning on this coming Sunday.
That was, apparently Kelly says an honor.
And it's just the suit.
What's the coffee there for? We get an opera copy to do that. I think I've heard about that. It's pretty cool. It's a very interesting topic.
It's a technical report so far. Hey, I'm going to bug you after this about scheduling a meeting. I figured I'd leave you alone until you gave your postdoc talk. We have a B3 on the 21st. We have a telecon on the 21st, but Jim and Alan wanted to have just local meetings. And, probably try to get the grad students to come. Yeah, so it's just a matter of
Got the money for the home, smart home, sustainable.
Yeah, you mentioned that back in December.
Yeah. So it's going to start going any minute.
Okay. Can we use the money to renovate my house?
As long as it's on the UBC campus, we can run demos. We can run demos in there anytime.
Hey Bob, wake up!
Everybody's welcome.
Here comes the robot. It's the anytime part that really worries me. Like 6 in the morning.
The anytime, yeah. Well, he works late at night.
Another do.
I know. Eventually, yeah.
I'm not signing up yet, but we'll see.
We can wake Bob up and
If it's a free novel, UBC campus, why not?
Yeah, exactly.
watch out for this guy here. He's one of those nasty guys from MIT. They have a reputation of harassing.
I think that helps me.
Not suffering fools, but
Yeah,
when I got through my talk at MIT, oh, they didn't give me too hard a time.
yeah. You had a doctor.
No.
But
There was a day.
It wasn't, I mean, there were groups that are worse, for sure.
Backlog list.
There was some groups that just go.
There are other
Fresh meat.
Also depended a little bit about who was visiting. We had a big Israeli contingent, and I mean, my experience.
Yeah.
And,
Which was
yeah.
They were talking about Israelis.
Oh, they're talking about
Oh, yeah.
Oh, my God.
And the Russians, too.
Exactly. I mean,
The worst is the Russians.
Israeli Russian, yes. We had plenty of that. But more than anything,
They're Google.
how hard it's trying to get each other to the lab.
Oh, yeah.
Sort of hopeful.
I mean, it was not uncommon. Again, it's sort of very, this old fashioned mentality. A lot of my coworkers, I got used to basically shouting. It's like, no, what are you talking about? No.
In terms of fitting into overall.
Well, so watch out. He's well trained.
I'll say
Sort
something.
of part of it is agree with you.
I guess Ella is not coming.
Doesn't have.
What time do you have? Yeah. Well, let's get going. I don't think it's useful to set a precedent for always delaying. You all come down to the front if you want to, but if you want to stick around back there, you certainly welcome to do it. I'm Jim Little. Ella asked me to introduce Junaed Sattar, who's my postdoc. He came here from McGill University in December a year ago, so he's been here just a little bit more than a year. And I guess this is the inaugural postdoctoral lecture series talk. So
Yes.
who better to do this than Junaed?
I can think of a few names, but yes.
So I'm not going to stand too long between you and Junaed's talk, but he works in a broad area of human-robot interaction. So he works with humans and with robots, and of course robots encompasses all of computer science. It's a sub-discipline of the physical-based computers. So you get to program, you get to interact, you get to plan, you get to decide, you get to do everything. So I think the talk will have a little bit of everything.
Pretty much, yes.
Okay, so let's go right ahead
Okay.
to this.
Well, thank you so much, Jim, for that kind introduction, and Happy New Year to everyone, and thank you so much for coming. I'm Junaed. I'm a postdoc with Jim, as you mentioned, and I actually ended up here. The red button, okay. I hope it doesn't mute everything else. Am I still okay? Can you hear me? Okay, great. I actually ended up in Vancouver right on New Year's Day last year, so it's been a year and 2 days since I arrived. So what I'll be talking about is a different set of approaches for human-robot interaction, which implies that there will be a lot of robotics. And I'll also be talking about my doctoral work and how it segues into work that I'm doing with Jim, and of course, recent work's been that I've been looking at with Professors Mitchell and Mackworth on a smart wheelchair project, but I'll get into that. So the summary of this talk is about creating intelligent machines that work with humans. And humans, basically the broad scope of this work addresses robots in arbitrary environments, so anywhere, pretty much. This is an example of what I'm talking about in a really harsh and hostile environment, which is harsh and hostile even for humans. An underwater robot following a scuba diver trying to assess the marine ecosystem out in the open ocean. So this is just an example of what we're talking about. Robotics as a whole is embodied by a classical sense, think, and act cycle. So we have a set of sensors that sense the environment, sense the world. Then we think, as in we process that sensory information and we decide, make smart decisions, ideally. And then we act on them, we locomote, and then we manipulate, and so on and so forth. And it's a branch of science that's advancing quite rapidly. And it's also becoming quite ubiquitous because robotic technology, not in the form of robots per se, but in terms of mobile adaptable technology, is being used more and more by the society these days. And of course, that implies that there's a further higher degree of human acceptance as time goes on. But there are questions, there are limits of our technological breakthrough, what can be done and what has been done and where we should be looking at. So this last topic of technological breakthrough is what we're looking at. So what kind of technologies for human interfaces are necessary or are, should we be looking at? So we're looking at technologies that can make your household robot or your lab robot bring its research papers to the grad students who are not willing to read them and basically say, you have to read this paper. Or you're looking at a robot working with scuba divers in the open ocean trying to map a marine ecosystem, like coral reefs, and look at how global warming is affecting water quality and so on. So these two pictures basically encapsulate my work in robotics till date. So I will be talking about mostly robotics in a human-centric description, but we'll also be looking at a few side topics, if I may say so, about the systems that actually drive all these robotic technologies. So these robots are called complex interconnected entities, electromechanical systems, and also there's a strong layer of software that actually gives intelligence to these systems, intelligence in a computational sense. And I'm not an electromechanical person, so I'm not going to talk a lot about that aspect of it. But the software system is actually described by the low-level reactive systems that drive the motors and that drives the robot and controls the system per se. And also there's this behavioral layer which provides robots the abilities to work with people, provides processing technologies for sensors, including machine vision, helps us, or humans, and the robots to engage in dialogues and learn activities of people around it, and also ensuring safety, doing all of that. So this is a summary of what I'll be looking at throughout this talk. And as I said, these topics encapsulate robots not only in your household, it could be underwater, it could be on the surface, it could be unmanned aerial vehicles flying over, doing surveillance tasks or mapping. So my personal work during my PhD was centered around this robot called Aqua. It's a 6 degrees of freedom hexapod amphibious robot that actually could walk and also swim underwater up to a depth of about 150 feet. So it's not a deep diving vehicle, but it was propelled by these unique flippers, as you see. And it has its own power on board. So we could completely untether it from any external power sources and let it go and guide it visually. It's primarily a visually guided robot, guided by machine vision, but it also has inertial measurement units, some depth sensors and depth gauges, GPS sensing, and also proprioceptive sensors that measures its internal currents and motor status and all that. That also comes in handy. There's a broad range of research going on even as I speak currently, are centered around this vehicle. My work focused around using machine vision for navigation and human-robot interaction, especially with scuba divers. That said, the proprioceptive sensors that I mentioned here were used by the robot to determine the kind of terrain it was navigating. So whether it was on a beach, whether it was on a carpet, whether it was on a snow-covered terrain or underwater, it could tell by just simply reading the machine currents, which is not part of my work. It could be teleoperated, or it could be working on a fully autonomous mode, guided completely by vision and human interaction. This is a very quick cross-section of the system that actually drove it. The summary, as it's presented here, looks at the two computing units, one for propulsion and one for navigation and sensing. And the propulsion system were these flippers. The flippers could swim while they were underwater, and the rigid nature of them could make the robot walk while it was on the ground. Now, the sort of system coverage that I'll be giving out is that the vision processing and the gate control, these two computers, were connected to the overall system over FireWire, which is the IEEE 1394 protocol, providing us with high bandwidth. This has been currently phased out to a gigabit Ethernet system, but this is what the current system was when I pretty much left the lab. And for a computer science perspective, if you're wondering how much coding it takes to get a robot like this going, and in terms of implementing your work, this is a breakdown of the lines of code based on language that actually is implemented on board the robot. So roughly about 90,000 plus lines of C++ code alone that drives the human-robot interaction system, not the drivers, not the propulsion. This is just the work that I've been doing over the past few years and the implementation that it takes for the robot to embody all those technologies. Now, so human-machine interaction is what we'll be talking about mostly, as I said. And the goal here is to have an autonomous vehicle which would act as what's currently been called as a co-X. X replaced by your favorite action or your favorite role. It could be your colleague, it could be your co-firefighter, it could be your co-photographer or co-marine biologist, and so on and so forth. So we're actually looking at a robot acting as your assistant or your partner, almost in the same role as a human would be. And of course, it kind of implies that we have to have intuitive communication protocols that could work anywhere and everywhere. So we could be doing underwater surveillance or underwater exploration, and that would be me working with that robot. Or it could be a PR2 in our household environment in the lab, and it would still be able to use the same technology, same set of technologies to interact with the human. Or it could be the Geminoid, who looks and acts almost human, but doesn't have much in terms of locomotion. Now, that said, all of these technologies are based on sensing. Sensing that are basically of two types that we can think of. One is some things that comes from biology. It could be visual, oral, sensing by touch, sensing by smell that we all possess. Excuse me. Or it could be some artificial sensors that are more robust, more powerful, but addresses a different niche of the sensing spectrum. It could be on lasers, radar, positioning systems. It could be your cell phone or Wi-Fi. We have decided on using vision, and this is work that I'm currently contemplating with Jim. Using vision as a tool for human-robot interaction gives us these benefits. It's natural, it's inexpensive. Inexpensive in the sense of the hardware that we need. You can buy a $100 webcam and it could do lots of interesting things. You could buy a $150 Kinect. It would provide you with a broad sense of abilities as well. And of course, these technologies have to come at a cost that is computationally feasible. The robot cannot have an indefinite amount of time to process and act on the sensory data that comes in. So the computational considerations are also very important. And one of the intuitions that actually come from is these hand gestures that scuba divers commonly use. This was taken from one of our field trials of the coast of Barbados. These two divers are actually interacting among themselves during the field trials using these hand gestures. So if anybody who does scuba diving would know there are certain vocabulary. There's a whole vocabulary for communicating between scuba divers. And that's where our work basically stemmed from. Can we mimic this? Can we do what the scuba divers are doing and translate it into robotic technology? Now, the problem with there is that the free-form hand gestures are quite difficult to translate into robotics or into automation as well. And it kind of spans into a whole PhD work by itself. But my work, or my intention, was to work on robotics. So we're going to bypass the free-form hand gestures interpretation completely and use something based on fiducial markers. These are tags. I guess everybody has been quite familiarized with QR codes these days. Those square pattern tags that look like barcodes, and interpreting or embedding signals into them that could be interpreted by the system quite efficiently and quickly. So that spawned off two technologies, two approaches towards HRI, or human-robot interaction, where we have a direct communication between a human and a robot based on these gestural languages or dialogues. You're talking to a robot, robot's talking back to you. Or we could have an implicit communication where a robot implicitly decides what you're doing and infers your actions and thus goes about executing its tasks. So it could track people without explicit signals, or it could understand activities without being told what the person is actually doing. And the technologies that we looked at were to replace those free-form hand gestures, as you can see on the top, to operate a robot underwater using barcodes, barcode-like patterns that you see in the middle. And that spawned off this three-layer architecture. So we're looking at a whole set of language, or a whole set of algorithms for humans to communicate with robots and vice versa. And this includes gestural communication, this includes people tracking, and of course the robot needs to find its way around the world, navigate, be safe, and not collide with obstacles, so on and so forth. So the key point here was this little block in the middle, where we have this three-layer or three-frequency-based system, where the most frequently called systems are the ones on the left that we call the high bandwidth systems. Systems that must run quite frequently for the robot to reliably perform, and the low bandwidth systems are the one that it needs to perform every once in a while. But these are the ones that are computationally more expensive. So we hit this trade-off between computational cost that increases as you go from left to right, and the frequency of its execution, which decreases as you go from left to right. And the algorithms kind of fill in all these little boxes, and that's what we're going to go into. So what could we do with this? Just to give you a taste of what has been achieved so far, we could talk to this underwater robot using those little one-shot tags. So the robot knows that, okay, it was told to go ahead and find the next person, and the next person shows it a different tag, and the robot goes out, maneuvers itself differently, and then goes out and does something different. Or you could even extend this to a whole set of programming on land or even underwater, where you're showing one command after the other, a whole programming language or a whole program given to the robot, that then you basically forget about it and the robot goes out and does its task. And this is again demonstrating how the same algorithm, same technology is usable in different approaches. As you see, I basically took off the other way and the robot goes out and does mapping and environmental sensing and whatever it's supposed to do. So this is just a quick review of what we have been doing with this. And the core of this work, this dialog system, was based on this language that we call RoboChat. Now, what does RoboChat look like? This is a comparison between something that looks like C on the left and something that we developed using RoboChat on the right. It's a reverse Polish notation language, which means that the operands precede the operator. So the code on the left and the code on the right do exactly the same thing. This is basically a loop that makes the robot do certain actions. What it does is not the key point here. The point is that if you look at the number of tokens on the left versus the number of tokens on the right, we could do the same exact things with 11 tokens with RoboChat, where in C-like language it would take about 38. And the goal was for a human, particularly a scuba diver underwater, have a minimum set of tags or minimum set of gestures to operate a robot and yet do complex things. So we wanted to expand this, what I would say, expressiveness of our language, but also keep the tags and the tokens, the language set, to a minimum as we could. And as I said, we used these barcode-like markers, circumventing the problem where we had to decipher hand gestures, and there's a high error rate in that. Instead, these are easily detectable by computer-based vision systems, and then we embed these tokens, and the language can be expressed with this. That said, RoboChat does not really need any form of, any particular form of tags to operate. It can work on any form of communication that you can think of. So how good did this work? So I'll just give you a brief results summary of what we've been doing. We performed a whole set of human interface experiments where people were actually asked to sit down, program a robotic system in front of a computer, and then we measured their times and accuracies. So the red bars are the systems where we use tags together with RoboChat, and the blue bars where people use the free-form hand gestures based on RoboChat, but interpreted by a human sitting in a different room looking at you at a little video screen. And the blue bar, the key point here is that has no computer automation in terms of interpreting its signals. So what we see here is, the summary of this slide is that the RoboChat is slower, or this tag system is slower, but not by much. Even the best user, the best user, which is me in this case, has less than 10 seconds of advantage when I'm using the hand gestures and making no mistakes. The worst user takes about the same amount of time, and the difference is also smaller. And in average, it's still around 8 to 7 second mark to program a really, really long instruction set. And you have to keep in mind that the tag system is not being interpreted, the hand system is not interpreted by any computer-based software. It is just another person who's looking at you and then writing down what you're actually saying. So this gave us hope that, okay, so if we can use this, and if it provides us with this degree of correctness and robustness, then this could be used for programming this robot for multiple tasks. And also, the adoption rate, like how good do you get over trials? So this is a set of 10 trials that we did, just to simplify the graph. Trial 1 to 10, this is a progression, and the time plots, as you can see, it varies a little bit, but looking at the left and looking at the right, the number of seconds required to program reduces quite a bit as you use this more and more. Unlike for me, which is represented by the green line, it's not much of a difference because I'm already out of the system. But when somebody who doesn't know anything about it is exposed to this, the more you use it, the better you get. So it's not something that has a very difficult learning curve. So moving on to what we could do with this RoboChat thing, or how we could instruct robots to do smart things. One of our goals was to use the robot to be a diver's buddy. If anybody here scuba dives, you know that in open water, you're not supposed to go out and dive by yourself. You're supposed to have a scuba diver buddy with you to ensure safety and make sure that your oxygen doesn't run out and so on and so forth. Marine biologists, who were one of our largest collaborators in this work, often go out for over 6 hours of time to look at marine coral reefs or species of fish migrating between reefs and see how their behaviors change over time. And staying underwater for 6 hours with a couple of oxygen tanks is sort of dangerous. So what they wanted to do is to have a robot do what they were doing, but the robot had to somehow learn or follow them for the first time and then figure out, okay, so this is how we're supposed to do it, so the next time we could do this autonomously. So the key point there was to have a flipper following algorithm. As in, can we follow a scuba diver underwater using vision robustly? I'll talk about tracking in a few more slides in a few minutes, but one of the major problems with tracking underwater is that the visual quality, the water quality, and the light variations, the lighting variations really affect what you're looking at, how the cameras perceive the world. And we had to come up with a feature that was robust under all these lighting changes or variations in visual conditions. The key point was the feature that we actually picked up was the diver's flippers. And this is something we call Fourier tracking. So what does it actually do? So here's one of our aqua robots. We had a few of these. Following a scuba diver, this was off the coast of Halifax on a September day. Pretty bad visual conditions at 30 feet. And the diver's swimming out in the front, and you can barely make him out in this video. Now what we're looking at from a rear view perspective, or the follow camera perspective, is that here's a scuba diver, here's the robot, we want the robot to follow the diver as he's swimming. And the robot has a view of the diver that looks like this. Basically this is, if you just saw this image, there is no way for you to tell that there is a flipper in there. So color features or other shape features are completely blurred out by the water conditions in this case. So what we focused on instead was the flipper's beating rate. So there's a huge amount of literature available in the world of marine sciences that look at human swimming gaits. And the values that we look at there are between 1 and 2 hertz is the rate at which the flippers actually beat as you're swimming out. So we try to look at features or images or video, length of videos that from which we could extract these features of oscillating intensities. So what happened was, we looked at these sequence of image frames over time, and we tried to find these little sub-windows where we could find diverse flippers. But how did we do that? We're basically looking at these different directions across frames to locate the diverse flippers by looking at the variations of intensity. So in this little box that you just saw in the previous slide, this flipper is going to go in that box and come out of that box at a certain rate. So sometimes the intensity is going to get darker, sometimes it will be brighter than what it was. So across these different directions, if you look at this, then we have what we can call as intensity variation, a sinusoidal intensity variation that looks like this. And that's what our data basically showed us. That in all of these windows, in one of them at least, we should be able to see a variation of intensity that looks like that. And if you pass this through a Fourier transform, which takes this spatial domain signal into a frequency response, we see these very high responses in the low frequency bands. So this was our signature. So this is what we're looking for, that in this frequency domain, can we see these little sub-windows over time that exhibit this high frequency responses, high amplitude responses in the low frequencies. So what does it look like? You see this, the green line that we're looking at on the top image, this is just one screenshot of this diver swimming out across the pool where she has been. This is her trajectory. And the red line basically indicates where she has not been. So the green bar over there shows the frequency response of the path that she followed, the intensity variations in the frequency domain. But the frequency bands where she has not been, for example on the red line, looks like that. So it's very, very different from where the diver's been and where she has not. So this gives us a pretty good signature of where the divers can be located. So when we put this on board the robot, this is what the outcome is. So the red square basically looks at the diver's location based on the frequency of the flippers beating and the responses that it produces. So even with all the different flippers and different body parts swimming, it's just the flipper that it's interested about. And based on which flipper produces the highest response, the tracker is actually switching between those two. So this is one of these algorithms that we used in the implicit algorithm bench, where we can use vision on board a robot to figure out people's swimming gaits and make the robot underwater follow it. Of course, as I said, that we could also use other features to track. And one of many different approaches is to use learning algorithms. Now, the key feature that we often look at is color. So underwater, we're trying to train, or we're trying to see how good that pink ball looks like. And our goal is to produce that image in the center, where everything else other than the pink ball is blacked out, and we have a little blob that shows us the location of the pink target. That's our interesting point. Now, in the normalized view, in the bottom that you see, is what we have, by normalized view, what I mean is that the intensities and the lighting variations have all been normalized, and this is what it actually looks like. So this is what the robot sees, and from that, given the properties of the ping ball, it produces a target that looks like this. Now, one obvious problem with that is that what if our object of interest is not purely pink? What if I'm not wearing a green shirt? What if I'm wearing a Hawaiian shirt, for example? Then there is a whole bunch of colors, whole bunch of distributions that the robot cannot rely on, because it will see colors all over the place. Or what if there's another pink target in the scene and the robot gets confused by that? So what we ended up doing was to learn the spatial distribution of color. Like, not just rely on one color feature alone, but look at how colors distributed across the space. And for that we use these little tiny filters. I'm using the term filters for these, but these are regions. These are square regions across the image space. You could look at one region, or you could look at regions side by side, vertically or horizontally oriented, or even these rectangular phases that look at color distributions and how they're their values vary across different objects. So once you have these filters, what you do with them is you load labeled data that says that this is our target and this is our background. And you feed it to an algorithm called AdaBoost. So people who do machine learning should be quite familiar with this term. I'm not going to go into the detail of that. But what AdaBoost is basically doing is it's voting. It's taking little tiny filters like the ones that I just showed in the last slide, and basically measuring whether that filter is able to separate or distinguish the background from the foreground. And it does that for a large number of filters. By large number of filters, I'm talking about 6,000, 7,000 number of filters at a time. And then it picks the best. It's a tunable parameter, like what do I mean by best, how many do I mean by best? And chooses those filters to apply to the image as it comes in. So what we do is offline, when the robots start running, we train our system with this labeled video samples, and then we have a set of these filters that we can use to apply in our online tracking scheme. And when the robot's working, then the input video sequence comes in. We have all these little classifier weights and all these little filters that are fed into that box, and the box produces outputs about the foregrounds or the target object's location as we continue tracking. So this is what we've been calling the spatiochromatic tracker, because it looks at spatial distribution of color across images. Now, what it actually produces, the learning step, is a distribution of different trackers. So this is one training sequence across multiple training sequences that we did. This just shows you the percentage of trackers that it picked. So the type 1 trackers are the ones that just look at one color. Type 2 and type 3 are looking at 2 and 3, and type 4 looking at 4 different types of colors in a neighborhood. So this is the spread that we're trying to learn. This basically says that for the training set that I've looked at, the best trackers, the mix of best trackers that we can pick should look like this. So we should have 36% of the single channel trackers versus 24% of the 4-channel trackers. And we should all use them together to have more robust and more accurate tracking algorithms, more tracking performance. And this is one set of results. We ran this across a number of data sets. I'm just showing 3 here for the sake of brevity. And in all cases, the boosted tracker actually produces better accuracy, as in how many times have I been able to locate the target object as opposed to the background, and it produces quite significantly better results rather than the non-boosted tracker, even across single color objects as well. And this is again a screenshot of a video sequence which is running this boosted tracker to track the diverse flippers, not using the Fourier tracker, but using the color features alone. Now, this is a black flipper, which is not the best color to track, and it still is able to find the flipper's positions, because when it's learning the flipper, not just the flipper's positions, but also the flipper's positions as it is surrounded by the color of her skin and also the water. So it's learning all of that. And as she swims further and further away, you can almost not see the flippers at all. It's covered by the bubbles, and it's covered by all these water disturbances. But even then, with the few little frames and the few little pixels of signal that are coming through, the tracker's been able to quite successfully lock onto her positions and then follow and the robot can follow. Right, so these two are vision-based algorithms that we've used, and as I went back, if I go back to the earlier slide when I said that there's an implicit set of algorithms that we can use for a robot to follow its human operator, or we can use an explicit system where the robot gets into this conversation with the human. So RoboChat was our tool for a human to communicate signals to the robot. Signals such as follow me or follow this person, can you learn color distribution, so on and so forth. One of the things that we didn't address till quite late was that what happens if the program sent to the robot was wrong or risky or somehow entailed degrees of danger that we are not willing to take on. And often in real life communications, there are problems arising from uncertainty and signal errors that creates risk in its task. So a cartoonish example that I've always given is that if you have a robot chef and you tell your robot chef to make sure that the guests are filled, meaning that they have enough food, and the robot chef here is killed instead of filled, it would produce quite uncertain, quite different results from what you actually intend to do. And that's, as cartoonish as it is, it kind of demonstrates what I'm talking about. So the goal here is to make sure of what was being said, what the command was, before we actually execute it. And how do we evaluate how risky and how costly it is? By looking at this cost-benefit analysis. So we do these two things. We assess the uncertainty in the command, and we also assess the risk in the environment. And then decide whether the command is safe enough for the robot to go out there and execute its task without causing danger to the environment or without causing danger to the people that are surrounding the environment. And this whole human-robot dialogue encapsulation looks basically in a cartoon form like this. The humans instructing the robot has to instruct back or communicate back to the human. And this communication is full of uncertainty because of noises in the system or mistakes made by the human. And also there are risks in the execution. Risks that can be to the robot itself. It could be a risk to the task completion, that we just cannot do the tasks in the end. Or it could be the risk to the people themselves, that robots' actions might put people in harm's way, which are basically big no-nos if you're doing any sort of robot deployment. So how do we end up doing this? So we end up doing this confirm before execute approach. So we make sure that if a task is too risky, we ask the human before we actually execute our task. So the robot seems to think that, all right, I was just told to jump off the 4th floor window. It should go back and ask, like, do you really want me to do this? And even better, you can actually ask targeted questions. As in, do you really want me to jump out of the window and not jump out of the door or something? And if the risk is still high, even after all the targeted questions are asked, then ask one last time before you actually go out and do it. So in a short form, this is not going to stop the robot from jumping out of the window if you really wanted to do it, but it will make sure that it heard you right before it actually goes and does it. So this is the flowchart of what our system actually looked like. We have on the left the symbol inference, which takes RoboChat-based language inputs, either in the form of speech or vision or any form that you can think of. And it does this inference based on a hidden Markov model, very similar to what speech recognition systems use, and tries to find out the belief of what was being said. And also generates a set of alternate sentences that you might have said to it. And this alternate set of sentences, that pushed back too far. This alternate set of sentences, together with the cost assessment from a set of what we call assessors based on the simulation engine, is provided to a decision function. So it looks at this costs and it looks at the belief value, or the probability of that statement being said for each of the sentences, and then comes up with a decision whether feedback is required or not. So this was the first version of this work, this HRI dialog work that we did. And we went through a set of evaluations where people actually sat down in front of computers again, programmed robots, and we designed this interface intentionally to elicit errors. So you could make mistakes and you could make costly mistakes, so the robot would have a chance to step in and ask questions. And then we went out there in the field where people would have to program this underwater robot with fiducial markers. And this is a robot's camera view of this experiment that was actually going on. So we had these tags, if I can pause this for a second. And these tags, for the sake of the divers, had these English language descriptions attached to them so they could know what was being said. And the robot was programmed using these tags so the robot could provide feedback or not, or just execute the task if it saw the task to be less risky than it needs to be. So the goal there was, if I can look back at it, was to not correct your errors, but the goal was to stop the robot from doing dangerous tasks without asking first. So this is just a brief summary of what we could do. The number of errors or risky errors on the right were quite high in the total number of experiments that we did. And in those, this is about 72% of these errors were stopped by the system, which were deemed to be too risky. So the user made mistakes or had risky commands given to the system, which is represented by the blue bar. And out of that 72%, were actually really, really high risk calls that the system intercepted and asked feedback for. The rest of the work or the rest of the dialogue that it didn't ask for feedback were still wrong, but they were not risky. At least for the robot's perspective, robot's risk assessment system, the robot would still go out and do its thing, but it would do the wrong thing, but it would not do something that was risky without asking first. So this has no error correction built into it. This has safety encapsulation, which means it was going to ensure safety before it executes. Now, recent work that we've submitted, we don't know whether it's going to be published yet or not. This is work here at UBC that I've been doing with Jim, has been to extend this dialogue. As I said, that instead of just asking for confirmation, we figure out what actually caused us or caused the robot to assess your dialogue to be risky. So instead of just looking at the feedback required part, we do what's known as grounding between the tokens in the language with what caused the risk in the environment. Approach that we label to as token versus risk grounding. So if you have a large sentence programmed to the robot or large program given to the robot, and somewhere in there you you make a mistake of a distance, for example, instead of 10 meters, you mention 10 kilometers, and that would make its risk assessment go spike quite high. We had no way to tell that before, so the robot just basically asked, do you want me to do this surely or not? And the user had to go back program the whole thing. Now we can actually figure out what caused this and just ask these targeted questions such as, really 10 kilometers? And then I would say, oh sorry, I meant 10 meters. And then it would just incorporate those changes into the system, reevaluate, and that would make its risk evaluation goes quite low, and then it would just go out and execute its command. Now, again, very similar to the last system, the expansion here is this token to risk grounding. And then the necessity here was that, especially if you have a very large program given to the robot, you don't want to reprogram again and again and again. That is just tedious and cumbersome, especially if you remember Windows Vista and this system they used to call, I don't know, error or some safety thing. Are you sure you want me to copy this file to your hard disk? At some point you just wanted to trash your hard disk out of the window because it was so annoying. This is what we're trying to avoid. We don't want to annoy the user to the degree that he just, oh, I don't want to do this anymore. But we want the user to be aware of the fact that he made mistakes and where he made the mistakes, so he could just correct those, as opposed to just give a wholesale feedback answer to him. Now, so that's one part of my work that I've been doing, and also trying to extend this currently here with Jim. This also plugs into this work that we're doing with a bunch of people based on the PR2 robot acquired together with Jim at LCI and also Professor Croft at Caris. So this is the PR2. For those of you who haven't seen it, this lives downstairs in the Caris. We call it Charlie. Charlie's got lots of different sensors. It is driven using the software layer based on the Robot Operating System, or ROS, which has been the very latest and one of the more prominent software layers in robotic technology in the most recent days. The good thing about ROS is that it stops what we've been calling reinventing the wheel approach to robotics. So all of this robotics research that's been going on almost addresses very similar work, but they're not always sharing code, or they're not always sharing their advances. ROS helps us to do that. So when we have a different tasks or different problem to address, we can rely on ROS providing us with a set of packages, black boxes that we don't want to open up and use. And in turn, while we solve a difficult problem on robotics, we have the choice to either release it open source or release our work based on ROS, and thus make sure that it's not forgotten about, or it is not, and that it doesn't end up in a position where you have to reinvent this again in the future. So this was quite nicely demonstrated by the PR2 hackathon team this summer. I can see Wesley sitting in the back. He has been involved in this. This is quite a brief video of the full video, which can be found on YouTube, where the robot was made to drive across labs, ride the elevator, and deliver mail from one lab to the other. So as you can see, the robot's quite able to navigate through narrow doors. This is a map view of what the robot's looking at, and navigating across rooms from one lab across the other to the elevator, finding obstacles and making sure it doesn't bump into them, or even people in this case. And then using its sensors, the laser sensors and the cameras and its arms to go out there and press the elevator button and go in and ride it. Now, this again has been a student project. We had a AAAI poster this year at the AI and Robotics Multimedia Fair. And I will also pitch the next version of Hackathon that is currently underway. So if students are interested in knowing more about it, you can talk to Wesley or myself and see how we're actually trying to extend this. What this work didn't have in it was an explicit layer of human-robot interaction. So what if there was a person in the elevator? What if the robot needed to go to the door but couldn't open the door because the door was too heavy for it? Could it ask for help? Could it find people that it could ask for directions, for example? So, which could be a controversial way of saying this, but we're also looking at using humans as a sensory input to the robot. Humans not to just interact with, but also provide directions to the robot. So this brings me to this man-machine network interface that also I'm currently working with Mark Grimson, who's an undergrad doing his undergraduate thesis with myself and Jim. And Mark's work has been to look at a set of sensors and robots to create this human-machine interface network that will help robots and devices across different varieties actually to provide better estimates of tasks and risks in the environment and get the work done as efficiently as we can. So going back a few slides when I talked about the risk assessment, what we've currently been doing, or till now what we've been doing, is having an assessment of risk based on the static environment before the robot executes its task. What we're looking at now is a suite of sensors using RGBD cameras like the Kinect, which not only provides red, green, blue images, but also provides depth, and Android smartphones and people as well, explicitly providing input to the robot to do certain actions. Now, these RGBD sensors have been quite popular in the vision community and in robotics. It can do gesture recognition quite easily out of the box. This is an open source software framework called ScaleTrack that literally out of the box takes 2 minutes to set up and can understand hand gestures and interpret them into languages. So this plugged into RoboChat helps us to avoid using fiducial markers or any artificial engineered marker systems to talk to a robot whatsoever. Or you could use the RGB depth capabilities of these robotic systems to provide better estimates, not just 2D images as you can see on the left, but a 3-dimensional model of the world as we're looking at it. So the robot can not only just find out where I am in the image space, but it can also find out where I am in the world space. So this is a 3-dimensional representation of me sitting in the lab trying to make this video. But it also gives you a 3-dimensional depth-wise representation of how things are oriented. But of course, there are the other issues about uncertainty in the environment that we have to address. So an Android smartphone, this is Google's own technology, not to trash this, but just to demonstrate what the problems are. I was talking to my phone using the voice technology to search for a certain restaurant at 6:45 in the evening on a summer day. And these are the suggestions that it was giving me. The last few were completely confusing to me because what I was actually asking for was this. So I used the phrase Dhaka biryani, which is a great biryani store, by the way, and it suggested that I go taco be doing, which has absolutely no relation to whatsoever. So this is real. This is not just made up. This did happen. And of course, there's an issue of accent, this is background noise, different people saying things differently. But when you're talking about machines communicating with humans, this degree of uncertainty remains, irrespective of what language, what modality we're using. And this also translates into work that we've been doing with Professor Little, Mackworth, and Mitchell on this project called CanWheel. The question that we're trying to address here is that how can we make a smart wheelchair, a robotic wheelchair, safely navigate in arbitrary environments? And not just a wheelchair, obviously, there will be a person sitting in the wheelchair. So this is a very high degree of man-machine interface bonding, if I can put it like that. And there's a completely whole new degree of interaction that has to be put in here. because we don't definitely want to annoy a person who's using the wheelchair with too many questions. So how do you design an interaction scheme? How do you ensure safety? The wheelchair doesn't bump into objects or roll down the stairs, but at the same time, the wheelchair helps you go to your table or helps you transfer from the chair to the bathroom or the chair to the bed. And how can we design methods that are natural to users in this specific domain? So this is the CanWheel team. This is work, as I said, with the professors here and also with students Ian Dawankar and Puriya Talabifard. And myself and Pooja Vishwanathan are the two postdocs involved in this. And the CanWheel team is a coast-to-coast team, basically spanning all the way from Montreal down to Vancouver. And we're working on, my scope of this is to work on these navigation methods and somehow algorithms that can ensure safe navigation using this risk uncertainty maze method that I've already demonstrated. And something that has nothing to do with robotics. Professor Lux has been kind enough to invite me to supervise this to a student of his on his master's work where we predict the outcome of cricket games. So if you're not familiar with cricket, this is sort of what it looks like, a complicated version of baseball, where this guy's not actually trying to hit this person, but it's often fun if you're, not fun if you're the guy with the bat, but interesting to look at. But the goal here is to have a prediction system which takes in the state of the game at any given point and then predict what the outcome of the game will be. So it's a coach's tool to look at the outcome and then have him make up a strategy that will basically reward the team that's using this tool. And as it might apparently have no relationship between robotics and this, there is a layer of Bayesian prediction and learning that we're kind of porting over from this task assessment stuff that we've already been addressing to looking at the situation and looking at the state of the game and predicting the next state. So there's a lot of particle filtering, machine learning, and Bayesian prediction involved in that. That is a quite common approach in robotics and vision. So in conclusion, I think I've taken enough of your time, so I'll wrap up soon. I believe that robotics as an industry is very much on the rise, and it's affecting our lives on a much higher degree as time progresses. And as a science, it just not only relies on other sciences or other sub-branches of computer science to contribute, but it also drives innovation, be it in vision, be it in software systems, be it in manipulation or planning or AI. And the goal here, at least in my mind, is to use robots to enhance, but not to endanger human creativity. And of course, to come up with newer methods of human-robot interaction in any environments across any robots, flying or not, that does not involve a person with an umbrella trying to whack that robot in case it comes too close to your being. So that's another good use of summer interns to make sure the robots are safe and not doing any harm to the lab. But that said, I will conclude with a few words of acknowledgement. So my supervisor and the team at McGill here at UBC, for the last year, I've had great support from Jim, Alan, and Ian has been working on the CanWheel work. Professor Croft houses the PR2. The hackathon team, it's been a pleasure working with them, and I'm currently doing so as well. Mark's been working on the human-robot interaction network, and it's taking good shape as of now. We haven't published anything yet, so that's why there are no published results, but we're hoping that can change soon. And the students from the CanWheel project, and of course Dave and Marius have been instrumental in helping me settle down in the lab. And my funding agency is the Quebec Research Agency on Engineering and Technology, Precarn, and NSERC. So with that, I'll stop and I'll be happy to take questions. Thank you for your attention.
Questions, please.
Do you do any wizard or bot studies in order to prototype certain types of interaction?
That is exactly currently that's what's going on with the CanWheel project. Myself and Pooja is the lead on that because her own PhD work was centered on the wheelchair and designing assistive wheelchair algorithms for autonomous navigation. So myself and Pooja, we're collaborating along with other members of the Canwheel project to create this Wizard of Oz study that will take place in Vancouver somewhere, I guess, in the summer and also late spring, to come up with this prototype algorithm, prototype interface. And in terms of my past work, we did a fair number of user interface studies that I didn't talk about here. Wizard of Oz, user interfaces, and the interfaces that we basically picked was a product of that study.
Can you tell me a bit more about how you develop the heuristics for the risk decision making?
Right, so the risk algorithm basically looks at a set of priors for the language that we use. So RoboChat, as we form it, has a finite set of tokens that the user can use to communicate with the robot depending on its context. So underwater, or in case of the PR2, on land and domestic environment. And we learn the priors based on the previous set of vocabularies, the previous sentences that have been used in programming the robots. So that's where the priors are coming from, which is fed into the HMM system, which predicts or generates a belief number, or the belief probability. And with terms of the risks itself, we have what we call this set of assessors that measure certain degrees of risk or certain aspects of risk. For example, is the robot traveling too far from its goal location to execute the task? How far is it going to go, provided that it's given a map? Or how deep is it going to swim? If it's, in the case of an underwater robot, will it exceed its depth rating? Will it run out of its batteries, and so on and so forth? So we're looking at these heuristics for risk and safety, and we're also looking at these probability values for belief that's based on the priors. So the heuristics basically are looking at a task simulation. So once the program is given, we generate a set of alternate statements, and then we run them through, not real time obviously, but we run them through this simulated engine that estimates these risks based on these heuristics, and then we combine them using this decision function. And then we pick one that's has the least, basically the goal is to have the task with the least uncertainty and the highest probability, and then we pick that. But in case of the highest probability task having a high risk, we generate a confirmation. So if we have a 97% probability of this task being said, but it also has a higher degree of risk, then we ask confirmation from the user. I don't know if that addresses.
Yeah, so if I understand correctly, the risk is defined as by impact and probability, and you're looking at, based on task simulation, a deviation from that
Right.
chain of activities.
Yes.
So then if it's deviation from a goal, is it deviation across, do you calculate the deviation across a set of chained activities?
Yes.
Or is it deviation at any one part along the pathway? How is that?
So the deviation or the risk calculation, as I would say it, is across the whole chain. So once you start programming, it's not just one part, but the end result is at the end of the entire chain of commands that were given to the robot, and then we calculate like how risky is this command be, how much have we deviated from what the norm is, to put it like that.
The reason I ask that question is, like, let's say you have a fairly complex chain of activities, and a particular link in that chain, it takes up a very small proportion of the chain of activities, but actually a deviation from that part of the chain is actually highly risky, as defined by perhaps impact.
Right.
Or even probability, like there seems to be a large probability that
Right.
the activity is not occurring as it's expected. So how have you anticipated that, and how do you address that in how the robot responds or predicts something as being risky?
Right. So I'll give an example of what we've looked at, given what you just asked. If, for example, one of the common tasks that we've tried out in the field was for the robot to swim up to the surface, take a GPS fix, dive at a certain depth, locate or acquire a diver, follow him for a certain number of seconds, because at the given time, and even now, we didn't have 6 degrees of freedom state estimation, so we couldn't tell how far we've actually traveled other than taking a GPS fix, which required the robot to surface. So we made sure that the robot would follow the diver for a certain number of seconds, and then break off, take images, and then surface. So a few sequence of steps. In that sentence, there's this bit which says follow diver for n seconds. Now this n is something that can throw off the risk value in a large value. I mean, I'm putting this as an example, and I'm asking you back if that demonstrates what you're asking in this case. Conceivably. So in this case, what we're looking at is we have this robot's norm operating region. And the robot's given its characteristics or operating procedure and everything. So in case of n being 60 seconds, 2 minutes, it's still fine. But instead of 2 minutes, if by mistake the command was an hour, that would throw it off completely, because it would translate into a large number of hours that has to be the robot has to operate underwater. Translates into battery consumption, CPU load, underwater sustenance, so to speak. Also for the diver as well, because the diver has to swim for 2 hours. So risk for the human, risk for the robot, risk for task completion, because the batteries might run out. All of these things contribute into a risky impact, and that will flag it. So that's what we've done, and that's how we've handled this. So the impact is not just one aspect of it, but these assessors are cumulative. So at each step, we're applying these assessors, and they're accumulating the risk values. So if any one of these assessors are assessing this, okay, so this is too risky, it will still cross the threshold, and the sentence would be flagged for confirmation. So that's how we looked at it.
So then I don't want to take over.
No, of course.
There's so like lots of different interesting avenues to go down when it comes to risk.
It is.
Then if you calculate it that way, in a cumulative, taking each particular calculation cumulatively, that allows you separate values for each, but doesn't necessarily account for the interaction of different risks with one another.
No.
And the fact that could also increase the risk. So let's say, 2-minute deviation in your example, 2-minute deviation is acceptable. We know an hour is outside of, that definitely would be flagged. But let's say there's a 2-minute deviation is allowed. But then the next task is that the robot has to connect with a diver that is coming through, and maybe there's some current involved or whatever. So there's something that has to happen within a time period, and if that doesn't happen, then somebody can't be rescued or whatever the scenario is. And so the 2-minute deviation actually creates a failed connect on that, the path crossing, and then that has, permutations and combinations down the decision chain or the chain of action. So I guess, one thing to consider would be in the heuristics, and this is a very tricky proposition, is whether or not there's a way in which the interaction of the different risks can be somehow accounted for in the framework, the decision-making framework.
Right, and I completely agree. Like in this model that we have, we don't have one risk unless it's implicitly modeled by it. For example, going by the previous example, like 2 hours of running time would increase the risks of the batteries failing and everything. But we don't have a risk evaluation at a given step directly relating itself to a risk in a later stage of a given sentence. What we do have right now is an instantaneous risk calculation and instantaneous flagging of tokens or grounding of tokens with these risks. So we know what caused the problem, so we can give a feedback to. But yes, we could easily envision more complicated tasks, especially if the language itself is more natural form as opposed to having a little more structured form as we do with Roboat. There's a body of literature on that, especially coming from the computational linguistics community, which I'm not an expert at, unfortunately, but there's a lot of work going on in that aspect, especially when you're communicating with, for example, an onboard car navigation system, and it's trying to feed back responses to you. And it's an open problem. It's a very open problem. There's a lot of work being going on. There's a lot of work being done, but it's definitely an interesting approach that I have not looked at. So my short answer after all this long detour would be that it is definitely something to be looked at. We haven't looked at it yet. And as of now, I don't have a very good idea of how we could model this system with this temporal risk assessment in the future, but it's definitely something we can look at. Sorry.
Just to continue on the same vein, but maybe stepping back a bit. It seems that this is an excellent excuse to introduce a software architecture which, at all levels, from the ground up and laterally, includes the elements of goal versus danger, like an anti-goal, and risk is going in the wrong direction, of course, towards the anti-goal. Certainty, contention, wherever, like throughout here, there's always a possibility of introduction of doubt.
Yes.
And doubt has a cost, doubt has a consequence. If it's an infinitesimal doubt, it can be ignored, and there are thresholds for vast changes in activity if the doubt is sufficient. And recovery mechanisms, obtaining more confirmation unless, as you said a couple times, you're annoying the human just too much. So this all seems to be unified. You have one slide, this algorithm flow, I think was the title, and you only had a correction coming out from the first box, which I think was command recognition or something.
I'll go back to it in a second.
The second box was something about Markov. Not that one. There were three rectangles across the top.
I'll go back to that one then. This one, I believe.
There you go.
Yeah.
And how you can have uncertainty coming down from symbol inference, symbol recognition, but not from program inference. Like in your Markov model, if one is an absolute clear winner, sure, go with it. If two are contending and very, very close, that's an introduction of uncertainty.
Yes.
Something should be done about it.
Right. So I should clarify this. That's actually where it's coming from. While we have the sentence coming in, then the HMM system is actually taking the sentence as is and predicting what was actually being said and producing a belief with it. And it also generates contentious options, as you put it like that. So it also produces a set of sentences, alternate sentences that could have been said as well, along with their belief values. So the uncertainty measurement, that's not just from the input itself, but also the inference of the input as well. So we do have these values.
Right. But back into my general purpose point of allowing uncertainty, quantified and multidimensional if possible, to be introduced at any point, at any level, and then having an aggregate percolating among, and when you don't know what to do about a form of uncertainty, in the case of a complex action, and it's only through the entire complex action that this uncertainty arises, have that learned, that you think you're doing everything right, and you fail, and so that should propagate back some doubt upon that process, end to end, and you just won't try that again if the cost was too great.
Right.
So, yeah, I guess it's seeing it as an excuse for developing an architecture in which these factors are throughout. It's done in what I've seen in communication systems where you have an important sensor, it produces results you can't rely on, and that has implications downstream. You just can no longer rely on whatever that module was producing, and maybe it's not that important, maybe it's crucial. And so in the past, at least, these things are all hand-coded. Like the engineer says, oh, by the way, if this happens, then you do this and this, huge system of rules to wade through. And a more general-purpose way of handling it is to have goals at all levels, risks at all levels, sort of as contending forces, and gives you a direction to choose actions. And uncertainties being introduced and having those knocked back for more confirmation when that's possible. It's sort of a unified approach as opposed to having skilled people or experienced people like an expert system, just write all kinds of rules at all these levels, and they're not really that integrated, and you've got a lot of complexity. So.
Yeah, that I agree with. One of the things that we're also looking at, not extensively yet, but this is a bit of user modeling as well. User modeling and learning, the application of learning in this unified system. How do you learn from experience, so to speak? And how do you learn about the user who's using the system? This is more relevant to, for example, the smart wheelchair, especially if it's modeled for a certain person. And you learn to tailor your feedback, tailor your confirmations and your questions over time. That whether it's being liked or whether it's not being liked, whether it's necessary, whether it's not. There's a big open area of learning about user behavior and learning about system performance. And how do you couple these two things together and then produce feedback or not, or take steps together. But I think that's one of the, another of these plugins that can plug in into this, this unified software framework that you mentioned. But yeah, that's a definite possibility.
Okay, let's cut off the conversation here. It's been great comments. Thanks very much. I'm sure Junaed will stick around and you can just do one-on-one afterwards. Thanks very much.
Thank you.